But I think essentially I'll try to give our perspective from a contractor's point of view. I've suffered a fair bit of pain over numerous jobs over some of these aspects. So just a general overview at the start of what I'm seeing at the moment, and one of the first issues is a trend towards the client setting lower peak temperatures limits in the specifications. So previously in New South Wales, the peak temperature limit was 80 degrees, and a couple of years ago it was reduced down to 70 degrees. I know in South Australia it's been reduced to 70 degrees, Queensland also 70 degrees, and Victoria, I think I've got 75 degrees there, but I'm not entirely sure about that. We've got numerous issues with these peak temperature limits on jobs nationwide, so I'll talk about a few of them in this presentation, but we currently have a project in Queensland where essentially we're just not able to achieve it. So I'll talk a little bit more. So, there is this, I don't know where this has come from. There's a perception that, delayed intricate formation in Australia is a problem, but you do a lot of research and you basically can't find many issues. So why has it been enforced? There's much other sort of issues when you look, inspecting older bridges that are, from alkali silica reaction and much more pronounced and documented. Just even the other night, just doing some research to find, what are the stats on delayed intricate formation in Australia, and there's basically hardly anything I could find. So, are we enforcing an almost impossible constraint to address a problem that doesn't really sort of exist? Not saying it doesn't exist or it won't exist if you do blow up the temperature, but I think for our general bridge and Super T construction that we're normally mostly exposed to, are we just pushing it too hard? And I'll also explain in this presentation some of the other issues that arise from trying to address these requirements, so ending up with less desirable outcomes. If you look at the probably the notable two pieces of research or standards on delayed intricate formation, there's in the UK there's the Building Research Establishment paper. They basically documented that any temperatures below 80 degrees will have a low risk of delayed intricate formation occurring. As you go over 80 degrees, it has an increasing risk, but then there's also research around that suggests that if you've got additives such as the fly ash levels above 20% or the slag levels above 40%, then you can reduce DEF up to temperatures of 100 degrees. So a lot of our concrete sort of mixes these days have these additives either as a minimum or we apply them. Syria C660, it's another well-known code or guideline. Also suggests that if you've got the presence of fly ash in the mix, reduces the risk of delayed intricate formation, and 80 degrees is acceptable for specifications. There's also, so I'll probably talk about, there's trend towards setting max differential temperature limits. So the issues with differential temperature is mostly with cracking, and this is reasonable. However, there's ways to control this, and so enforcing too many limits without any flexibility is probably sometimes not the best way to go. I think it should remain open to engineering controls, leaving it a bit more open. One of the other issues that is turning up on some of our construct-only contracts, the specifications apply the limitations in the specification, but there's, the design doesn't provide all the controls or the options to achieve it. So, controlling diff temperature, there's multiple ways that you can do it. Therefore, but you don't know the design because it's a construct only. So, you generally aren't engaging a design consultant in a construct only contract to deal with these sorts of issues. You're basically just pricing a job. So, how do you price these requirements? And we do have jobs at the moment where, you pour the concrete and differential temperatures exceed. You apply some sort of controls, but how do you know that? You're not the designer, so whether that's engagement of the designer during the construction phase, but you've already priced the job, so how do you then pay for all these things? So that's another issue that's not quite addressed. Also, you've also got for differential temperature, there's long-term cracking requirements, allow up to 0.2 mil to 0.3 mil cracks, which is reasonable if you look at all the literature that's coming out at the moment. RMS B80 specification has 0.1 millimetre as the non-conforming crack limitation. Now, the trend that we're seeing there is that the reason for that 0.1 mil crack width limit was generally to record the NCR, and basically become a monitoring process. Sort of in the future, you knew where all the cracks were, you come back and inspect them. But now we're getting enforced to start repairing cracks, anything that's above 0.1 mil crack widths, which is becoming an issue. So, if you've got differential temperature is hard to control. Things do crack. Concrete does crack. But when you get forced to just repair everything that cracks, it becomes a bit of an issue for us. One of the other issues is that we're also seeing on projects is a trend towards clients now nominating higher exposure classifications in the SWTC or design criteria. So the last job I was on, it said this is the minimum exposure classification is to be B2. You do all the environmental assessments and you realise it's actually only B1. But there's the perception that providing a B2 or a C exposure classification is going to give you the best outcome, and what we're finding is actually that's not really the case. You're bumping up the cement content, it's more likely to crack, it's more likely to get hotter. How do you achieve your peak temperatures? You've got all these conflicting requirements. So I just don't think things are, if you want a higher exposure classification, perhaps you then, in class B2 or C, maybe you do allow for higher peak temperatures and things to be addressed. So that's just a general overview. I'll probably talk about some of the projects now. Nambucca Heads to Yarunga. This is a thick blade pier over the Clang River. It's 9 metres wide, 2.2 metres thick at the pile caps, 1.9 metres deep. The actual pier component had a width up to 2.5 metres thick. So massive pour, something that's difficult to control. These were the requirements that differential temperature across any face must not exceed 20 degrees. We have to insert thermocouplers to monitor. The other requirements is measures must be taken for the heat of hydration using blended cements, cooling concrete during curing, insulated forms, and the use of large aggregates. Now we did all that, you still don't achieve the peak temperatures, but I'll continue on that. So on this project, the peak temperature limit was still 80 degrees, and as I said before, it's been reduced to 70. In this case, I think it'd be almost impossible to achieve. What did we do on Nambucca? We had early morning pours, chilled water, concrete admixtures, low placement temperatures, and our end result was 78 to 83 degrees. So it was essentially, some results were non-conforming because the limit was in that time 80 degrees, but if it was 70 degrees, you got no chance. Like it just wasn't going to work. So talking about differential temperature here, I suppose probably just explain the issues that can occur. So this is on the same job. You've got a pile cap that you've poured, and then you've gone and put another concrete pour on top. It gets hot. You've got a restraint there, so next minute wants to shrink as it cools, and as you can see, that's where you typically see some cracks. What do we do on this job? We had a requirement to pour the pier quickly after the pile cap. And we also used a higher density of reinforcement at the base. Now that was all modelled up, and we did all the assessments. But if this was a construct only contract, how would you have dealt with that? We could only deal with this because it was a D&C. Pouring the pier quickly after the pile cap. How do you place those limits in a spec? It's a bit difficult. The issue of differential temperature is, you've got the inside is hot, but then you have issues with the ambient temperature or wind, particularly is pretty damaging, which basically cools the outside surface. So you get quite a large, if you've got 80 degrees in the centre, you get quite a large differential to the outer edge, and that's what causes cracks for differential temperature. Now that is a real well, I wouldn't say issue, but it's a real effect. So what did we do on this job? I think you can see that picture there. It's not. Sorry, I'll bring it up. We used insulated forms. And the other thing that we did is that basically on this job we wanted to strip our forms quickly. Most contractors want to do that. Pour your concrete, strip your form, move on quickly. So what we did in this case is that we actually once we stripped the form, we quickly put on a thermal blanket. Now, these are actually pretty cheap to do. I think this one was made up with a bit of camping material and some of that sort of insulating sort of foam that you get, like a Softhlon or something like that. It's pretty cheap sort of stuff, but very effective. So I might go to the next slide. So this is the temperature graph for one of the pours that this is the first pour that we did. And as you can see, we exceeded at the top, we exceeded the 80 degree limitation. That was probably mostly due because our pouring temperature was above 26 degrees. So if you reduce your placement temperature by one degrees, the ratio typically to your peak temperature is a 1 degree reduction in the peak temperature. It's typically a 1-to-1 ratio. I also probably want to draw your attention to the green line on the right. That's the differential temperature. Now, as you can see, we had the insulated forms on, and it was very well controlled. At that point, that's where we stripped the form, and one of the issues we had is we couldn't get that blanket on quick enough just due to the construction methodology. It was the first one. They had a few stuff ups that didn't quite fit, and they had to, took them a little bit longer to get it on. And as you can see, that differential temperature with the outside face just started to cool from the wind and other things. So you can see that crept up, and we had a non-conforming differential temperature. So, and the result of that is we ended up with some cracking. The next pour, we got it right. As you can see, we got the placement temp was less than 26 degrees, so we managed to get under the 80 degree limit. And the same again, as you can see on the far right, you can see where we stripped the form, and we got the blanket on quickly, and it was just a slight increase. So I think the differential temperature there was only 12 degrees, so it was very well controlled. And as you can see, those thermal blankets, very effective. And the end result is no non-conforming cracks. So, you know, it is effective. I'm going to talk about the Oxy Highway to Kundabung experience. The main issue on that was that we had the 70-degree peak temperature limit imposed. So this was the first job that we had with this limitation. I'm not quite sure if you can see that column, but these are... So there's 12 piers on this particular bridge, and essentially what we ended up with is non-conforming peak temperatures for every single one except one. You can see on the left here, these are the different mix types. So, yeah, so maybe I'll just explain. Early morning pours, that was done. Chilled water was used. Placement temp was less than 26 degrees. This is mostly for the headstocks, so they weren't anything out of the ordinary, just a standard headstock. That's the only compliant temperature that we had, 66.5 degrees. But we didn't achieve the 28-day concrete strength, minimum strength. We were probably 5 MPa out, I think, if I can read that correctly. But what you can see is there's on the left there, for one bridge, we had 5 mixed designs. So how can you say that that's a quality outcome? You know, look at what was forced. Look at the way that we were forced to start with one mix, didn't comply with the peak temperature, another mix, where's the consistency there? There just isn't. So these are the behaviours that we're going towards based on peak temperature with mixes that have fly ash and slag in it for an issue that it's not really even going to exist. You know, it's just not driving the right behaviours, and I think I think that's kind of wrong in the industry. The only time we managed to achieve the peak temperature limits was when it got to the winter months. Again, another 2 mixed designs. We couldn't achieve it in the warmer months. It was only achievable in the cooler temps. But, you know, going back to this slide here, going back to this mix here, we dumped a whole lot of slag into the mix. Now, what that does, it slows down the chemical reactions a bit, and I suppose people will be able to, in this room, be able to explain things a bit better to me. But it does reduce your peak temperatures. But what you end up with is reduction in the 28-day compressor strength. So, you know, there's one way to control peak temperature, but then you just got another non-conformance now. So you're just chasing your tail. I know in South Australia there's issues with putting slag in the mix because it adjusts the, it's not the sorptivity, but I think it's the permeability sort of ratios or something. So again, you're putting slag in the mix and you're then sort of dealing with another issue. Basically, you just don't have much of a window to get through. So on Richmond River Bridge, after all the heartache that we had, we wrote a discussion paper. We managed to get a relaxation of 75 degrees. So if you're on projects, I recommend trying your best to get some sort of relaxation. The deal was NCR, but still recorded, recorded as, but it, agreed that it'll be accepted as is. So at the end of the day, you've got all the documentation. You can monitor things in the future, if need be. What are some of the engineering controls that you can deal with for peak temperature? Get a relaxation to 75 degrees, reducing your least concrete dimension. That's kind of another one of those things. You just have a direct impact on peak temperature. You could add internal voids. As I explained before, reduce the pouring temperature. So if you can get that right down, that's a good thing. I think one of the issues that we have in our job in KSD in Queensland is we're having to actually pump concrete by, 1 or 2 kilometres or something, and by the time it goes through and picks up all the friction, it increases its temperature by about 5 degrees. So whatever you pour it into the pump at, but at the other end it's another 5 degrees hotter, and then again you can't meet these peak temperature requirements. So it's quite difficult. Early morning pours. This is one for the concrete suppliers. Getting those aggregates in the shade, chilled water, ice. I know on the batch plan on Nambucca we started insulating the storage tank for the water and things like that. So that definitely helped a bit. All these little things, just to get little 1 degree here, 1 degree there. It does all help, but it's not easy. There's another trick in the spec. You can reduce your cement content by 3%. So that was another thing we did to get under that 80 degree limit on Nambucca. Just applied that directly. Reduce your exposure classification. Let the engineers do their job. Let the durability engineers do their assessments. Let them define the exposure classification. Don't just max it up just because you think you're going to get a better durable outcome. It just doesn't result in that. Slag definitely helps, but slows your strength gain. Yep. So as I discussed before, be careful with your 28-day concrete strength. Slow strength gain, so you can't strip. It means you've got to strip your forms a bit longer than what you normally would. So you're adding this to reduce your peak temperature, but then you get a program penalty. So you're addressing an issue that shouldn't need to be addressed, and you lose program. Another opportunity may be in the specification, maybe there's an argument to have the utilisation of minimum 28-day strength at the 56-day test. And the other ones are cooling convection tubes and water pumping or airflow. So on Richmond River Bridge, during the design, we did a lot of modelling. We used Sirius C660. Now, that can actually be applied quite poorly, I've noticed, in the industry. I think you've really got to be experienced and know how to model those things. In Sirius C660, there's a lot of errors that get made that I see in the industry, and so just be cautious of that. We went to the extent of using Midas, using finite element models to do the thermal modelling. 30% fly ash or 65% slag. We had a couple of options there. We got rid of the requirement to monitor in piles. Now that's another important one. I know on Grafton Bridge they're having a lot of problems up there trying to get their temperature down. They've got those 3 metre diameter piles. So, what do you do? Yeah, okay. So some of the other things, I'll probably talk about what we used on Richmond River Bridge helped us as well. These are our pile caps. If you can sort of see that what we have here, we had a precast shell that you just applied directly over the top of the pile. Now typically your pile cap needs to go to the depth where we've got the soffit there, but what we did was create that as a false floor, so we reduced the thickness of it. So that definitely helped us significantly to control the peak temperatures. And the other benefit you get is you've got a shell that automatically insulates that face of the concrete, so you don't have any differential temperature issues resulting in that. Yeah. So false bottom insulated. Yeah, so on the pile caps, we were enforced to use exposure classification C. The actual assessment was B1. Like once you did the assessment of the actual concrete on the inside, so the shell was C. That's fine. It was easy enough to do in the precast yard, but with that big thick concrete pour, it was actually B1. It's fully protected. There should have been no reason why we shouldn't have been able to use it, but we used Class C. High amount of cement content. We had all the additives. The modelling showed 70 degrees was just achievable. So I think in this case we do show that we did exceed the 70-degree limit. So, you know, with all those controls applied and all those sorts of things, you still can't meet it. Non-conforming. But differential temperature was controlled. So, in the columns, one of the things that we did was during the design, we inserted a steel column into the centre of the, basically just a 60mm conduit into the centre. It's hard to tell from this graph, but basically what that did was change the peak temperature location to be not at the centre, but changed it to be a third of the way from the centre to the surface. So it just kind of changed, and you know, on site when you after we've done the pour, you could actually feel the heat coming out of the centre of the tube as the as it was the concrete was curing. We got about a 10-degree reduction in peak temperature from doing that. And we managed to achieve compliance for all our columns, which was a good outcome. This is another sort of innovation we came up with. This is a precast headstock shell. So you just drop this straight onto the columns, pour the infill. You can see the section there. As you can see, fully insulated around. On land, it was B1 exposure. We were forced to use B2 over the river component. It was okay for program because we didn't need the strength gain. We didn't need to strip the form, so it was not an issue to have slag in the mix. Overland, generally the peak temperatures, this was a B1 mix, so generally the peak temperatures were in the 70 to 75 degrees, so we didn't meet the 70-degree limit, but we managed to write a whole bunch of non-conformance reports anyway. And as you can see, differential temperature was controlled because you've got that shell. The shells are pretty effective, kind of over the water. Even with all those additives applied, it was a B2 mix. We had instances where we ended up with up to 85 degrees. So that was not ideal. But it just shows you apply all these controls. You know, how on earth we were ever going to achieve 70 degrees, I do not know. So concluding remarks, peak temperature. I would suggest that 70 degrees is okay as your standard specification requirement, and adopt the advice from Series C660, such as if you have fly ash or slag in the mix, that there could be a relaxation to 80 degrees. I still think you need to have some sort of downward pressure on the contractor. You know, but and the condition to, you know, write an NCR so that in the future you can, you know, monitor the effects of delayed intricate formation. Differential temperature. I think the limitations are okay, but I would only say that allow some flexibility to undertake some modelling and apply the engineering controls. I think just having a blanket, you know, can't do anything, I think that's not the way to go. Obviously you can see we came up with some engineering controls, but reinforcement's also another way to control it. You might want to have that flexibility to have a quick program. Thermal modelling, I support the thermal modelling during the design phase, and it gives you a better understanding and assesses the options to apply your controls. So you can actually run a few options and you might be able to save a bit of money, save a bit of program, so I support that. Exposure classifications and the durability assessment. My view, we're required to do it in the design phase, in the D&C and design phase. You're required to do a durability assessment, but then you're not allowed to define your exposure classifications for those that are already. So there's a conflict there, I believe, and I think the engineers should be allowed to do their work. You know, instead of just adopting higher exposure classifications just for the sake of it. You know, we've got a design life of 100 years. Define the environment, do your testing. You know, we should be able to do that. Yeah, I think that concludes my presentation. I hope that gives you a few insights into the contractor's world.